Sorry about this. I forgot to start to record this. So let me just say what I missed because I just started recording late. We're dealing with linear maps, the properties of being linear onto and one-to-one, and we're building up to sort of the introduce the idea of the composition of two maps. So we have a map from A to B and a map from G from B to C, and if both maps are well defined, the composition is going to be well defined. And then I went off and reminded you what it means to be linear. And then we came back and what you mean by this is the definition of what you mean by composition. And a property of composition is that if the two maps involved are one-to-one, then the composition is one-to-one. If the two maps are onto, then the composition is onto. And last time we sort of ended at the point where linear maps that are one-to-one and onto are called isomorphisms. And isomorphisms captures the idea that two vector spaces are essentially the same. So, and the reason is because, or one reason is because the linear nature says the structure of each is the both. And the nice thing about isomorphisms is if we have, let's say that we have a map F from A to B, and let's say that F is an isomorphism. Okay, so if F is an isomorphism, so that these two vector spaces, that's what we mean by saying that A and B are isomorphic. If we say that they're isomorphic, that means there is an isomorphism. So suppose F is an isomorphism between A and B. That means it's a linear map and it's one-to-one and onto. Then the claim is, in this circumstance, the dimension of A equals the dimension of B. They have the same dimension. Okay? Now, if you remember, what's the dimension of a vector space? Well, it's the number of vectors in a basis. So what it's saying is if we have a basis for A, it's going to have the same number of vectors as a basis for B. Well, let's see why that's true. Let's say that the F from A to B is an isomorphism. And that's what we can say. Well, let's say we have a basis for A. What am I going to use for the name for the basis for A? Well, we have basis for A is a sequence of vectors. Say we have the basis. Let's just call them A1, AI up to AN. So if we say that the dimension of A, we say, just give it the name N, then say we have a basis for A. Well, if a basis for A, it's going to have, say, N, say 2 or 3 or 4 or 10 vectors in the basis. Here's the basis for A. We're just going to call them the A sub i's, okay? Now, so if F is an isomorphism, then it's going to map, because each of these vectors is in A, F is going to map F1 to some vector B1 because it's well defined, and that like F of A2 goes to some vector B2, and F of A n equals some vector Bn. And now, so we have n vectors here, and we're going to want to, if we could show that the Bn's, B1, B2, Bi, up to Bn, was a basis for B, and that all of these were distinct, So we'd have n vectors. We could show it was a basis. Then that would show that the dimensions were the same of the dimension of A was the same as the dimension of B. So how can we know? Well, first of all, how do we know there's n vectors? Maybe two of these are the same. Well, but since the A's are basis vectors, if say B I equaled BJ, if two of them are equal, well, that would mean that F, let's say it was like 1 and 3 to be concrete. Well, that would mean that F of 1 equaled F of 3. But then this would be the case where two vectors A1 is not equal to A3 because they're part of a basis, but the images were the same. Well, that would be contradicted by the fact that would be two different domain vectors going to one codomain vector, and that would be ruled out by the fact that F is an isomorphism. So not possible because F is 1-to-1. So that means we have n vectors here, one for each of them. But how do we know that they're a basis for B? Well, the only way we have to show if it's a basis, we have to show that this sequence of vectors, we have to show one, it spans B, and two, that they're linearly independent. And we have to do that without knowing anything concretely about the vectors, but just that that F is an isomorphism. Well, let's see if it spans B. Let's choose an arbitrary vector in the basis B, right? Any vector B. So how do we proceed? Well, one thing we know is because F is onto, that means that for any vector B in the codomain, there is a vector A, member of the domain, such that B equals F of A. We know that an A exists because F is onto, so there has to be a preimage, some vector in the domain that maps to it. But then A is a vector in the domain. So we have to be able to write it as a linear combination of these. So this has to be able to equal to F of R1 A1 plus R2 A2 plus dot 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 plus R Rn an. For some numbers, there have to be some numbers, real numbers R1, R2, R3, up to Rn, so that because the A's, the A1, A2, An form a basis for the domain. So any vector, so it spans the domain. So any vector has to be written this way. Because F is linear, we know that there has to be an A because F is onto. Because F is linear, we can write this as R1 F of A1 plus R2 F of A2 plus dot 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 Rn F of An. Well, but we've chosen the B's to be these. So this is R1 B1 plus R2 B2 plus dot 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 plus Rn Bn. Well, that shows that these vectors, the B's, span the codomain because F is onto and F is linear. You end up with the preimage A and B are the same, that like the image of B is the same linear combination of the B's that A is of the A's. So that shows that we've verified one, that these B's span the space, but are they linearly independent? So one is checked. There, it spans the B's The B.
Professor, may I ask you a question?
Sure.
So the example that you show right now that we have to find that the span of B and linearly dependent, is it correlated or it's connected to the previous one that you found that f of A1 of the vector A1 doesn't equal is equal to f of A2 of A3?
Yes, the point is that we started with a basis for A. We just chose this. We know that because A is a vector space, it has a basis. So we choose a basis. We know there has to, and it's an n. It has to have a dimension n. So we have n vectors. So we just say all we know about the A's are they form a basis. That means they're linearly independent and they span the space A.
But
And we
after you said it's not possible because f is 1 to 1.
Oh, yes, because the point is no, the point is that what's not possible is for two of the B's to be the same. The point of this is all BI's are different. In other words, I have f of A1 is B1, f of A2 is B2, f of AN is BN. But if this is just linear, if this is just a linear map, it could be that all these B's were the same. So what tells me that if I have n vectors here, why do I have n vectors here? I have n vectors here because the map F is 1 to 1. I can't bunch up. I can't have two of these that are different. Like f of
So
A1 and f of A2 can't go to the same vector because if it did, that would be so
onto
it's not so what's not possible is for those to be the same.
because that shows us that it's onto.
Yeah, that would show that it's not that would show that it's not 1 to 1.
But what does it show us?
It shows us that there's n vectors in here. All we know now is that the B's, that there's n of them. So if I have three over here, I have three over here, and they're different.
Okay, so but after how you assume that from 1 to 1 that f is 1 to 1 that we have to show that it's onto.
Oh, we know from at the beginning that F is both 1 to 1 and onto, because that's what we're assuming. We're saying, suppose that we have an isomorphism F between A and B.
And we're checking both to
And
see
we
if
want and we want to
they,
prove that A and B have the same dimension. So the
okay.
idea is we start with this and say, suppose that there's an isomorphism between A and B. I want to prove that they have the same dimension on this basis.
Okay.
I want to show if F is an isomorphism between vector spaces A and B, then the dimension of A is equal to the dimension of B, which means that the number of vectors in a basis for A has to equal the number of vectors for a basis in B. So I choose a basis for A and then I'm going to find a candidate basis in the images of my basis vectors for A. Those are the B's. And several things could go wrong. One is there might not be n of them. There might be if there might be 10 here, but only 5 here. But if that's the case, the way that would occur would be some of these would have to be the same vector. I have a B1, a B2, a B3, but maybe B1 is equal to B3. But I can't have that. That's not possible because F is 1 to 1. Because F is 1 to 1, I can't have F of A1 equaling F of A3 because if A1 is not equal to A3, if this was the case, I would have A1, A3 going to one vector here, and that's ruled out by the fact that F is 1 to 1, and that means that all the vectors are different. So I have n different vectors here. So if I want to show that that B has a basis of n vectors, I have to show, all I know now is there's n different vectors, but I want to show that those are actually a basis for the codomain B.
But if it's false for the 1 to 1, it's not true for the onto.
If I don't understand what you just said. You said
So so
if what
so
is if what is false, if what it,
So, so
yeah.
right now we found that it's not possible because f is 1 to 1.
When you say
Because we're
when
assuming it's 1
okay,
to
when
1.
you say it, what do you mean by it's not possible?
No, because you say under the A1 it doesn't equal to A3. That's not possible because f is 1 to 1.
Right.
But if we assume that f is onto, that's not true.
Okay, the ontoness doesn't the ontoness doesn't isn't this argument has nothing to do with F is onto, but that's not relevant to this part of the argument.
Okay.
I'm not sure maybe there's something um this is like saying so what how would there fail to be n vectors here? Well, it could fail to be n vectors if two of them are the same. But if these two are the same, if B1 is equal to B3, then B1 equals f of A1 and B3 equals f of A3. In that case, these would be equal, and since A1 is not equal to A3 because this is a basis, it's not, this is not possible. We have a contradiction and we can't have, this is impossible. B1 equaling B3 is impossible because F is 1 to 1.
Maybe I'm confusing myself because from the beginning we see that we're trying to find the isomorphism, as you said, is onto and 1 to 1, right?
Right.
Both can be both. So we cannot assume that if we cancel out one, it's the other, or it can be neither or both, or
Um,
no.
okay. I don't know exactly when you say cancel out one.
So right now we didn't find out that it's not possible because we assume that f is 1 to 1.
Yes. When you say it's not possible, what you mean is it's not possible for two of the B's to be identical because F is 1 to 1. These images must be different. There must be, you can't have two of them be the same.
Okay.
Is that okay? Maybe we see the whole picture because and the second part here we use the fact that we wanted to show, this is sort of part one. We wanted to show all we know now is we have n different vectors, and we want to show it's a basis for B. That these B's are a basis for B. Well, we've showed this first one just shows that these B's span the codomain. And then I was about to start showing that the B's are linearly independent. So if I take, let's say, S1 B1 plus S2 B2 plus dot 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 Sn Bn, and we suppose that that's the zero vector. We want to show that all the coefficients, all the numbers S1, S2 are all zero. We want to show that those are zero. That will show us that they're that these are linearly independent. Okay.
Okay.
So now all the B, these are the, so each of the B, so this is the same equation as S1 F of A1 plus S2 F of A2 because F of A1 is B1, B2 is F of A2, and S and F of Bn equals 0. So this is what we're supposing. Okay. Now, because F is linear, I can pull all these together and multiply in the S1s here. So this will be F of S1 A1 plus F of S2 A2 plus dot 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 plus F of Sn Bn equals 0. And then that's using the multiplicative property of linearity. And then I can use the fact that this that this is the same equation as f of S1 A1 plus S2 A2 plus dot 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 Sn Bn has to equal 0. So we have that this linear, oh, I'm sorry, that's A, this is the last one, F of, there are A's here, F of A and F of A and,
But the S doesn't equal to R.
yeah, these are just arbitrary numbers.
Okay.
We suppose for some S1, S2, Sn that they're equal to 0. So this vector has to map to 0. So we want to know what this vector is. Well, it turns out that in any, this is an aside, in any vector space, because F is linear, F of 0 gets F of 0 in A gets mapped to F of 0 in B. And so F of 0 is mapped to F of B, right? Okay, F of 0 in A is always going to be mapped to the 0 in B. Why is that true? Well, we can say what is F of the 0 vector in A is equal to F of the number 0 times the vector 0 in A, okay? Because 0 times any vector is oh no, it's this, because the zero times the 0 vector equals the 0 vector, because 0 times any vector equals the 0 vector. So in particular, it takes the 0 vector to the 0 vector. But then because F is linear, that's equal to 0 times F, the image of 0A, and 0 times any vector in B is equal to the 0 vector in B. So this is true. That any linear map maps the 0 vector in the domain to the 0 vector in the codomain. And it's a property just of this it's guaranteed by the multiplicative property that 0 times any vector equals the 0 vector. Okay? Well, given this result star here, we have at this point we have this result also. Well, if this vector was not equal to the 0 vector, the map wouldn't be 1-to-1 because we'd have two different vectors mapping to the 0 vector in B, right? So what that means is that S1A1 plus S2A2 plus dot 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 Sn plus S and AN. So the linear combination of all the vectors has to equal the 0 vector in A. Okay, well, the A's are a basis, so they're linearly independent. Because they're linearly independent, if this is true, then because A is a basis, S1 equals S2 equals S3 equals dot 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 Sn equals 0. So all the coefficients are 0. But those are the coefficients that we moved back to this one using F, but that's also the coefficients of this B. Therefore, the BI's are linearly independent. So we know that the B's are linearly independent. They span the space. So B1, B2, Bn is a basis of B. And because these are all distinct, the dimension of B equals the dimension of A. Okay, well, in the text, it also points out that we could also use a very similar argument to show that if the dimension of A equals the dimension of B, then A is isomorphic to B. That is, there is a one-to-one linear map that's one-to-one and onto between A and B. So what we'd have to show this, we have to do something. We have to do something we haven't done before, which is sort of now, instead of, this is true, but what I'd like to show you is that the action of a, you see, let me see, do it this. Given the action of a map on a basis, we get a complete linear map. So let's see, this is a practical matter. Let's go back to, I had this specific example up here of a linear map somewhere. Let's see, or maybe I didn't. Okay, let's just write down a linear map. Let's say I have a linear map G that takes us from X, well, let's take us from XY. I think this was the map anyway. X plus Y, X minus Y, 2X. Okay, so this is what I mean by the general formula for a map. Okay, it's the analog of f of x equals, well, let me use a different symbol. If I had a symbol s of x equals x squared, is a real number thing, I'd just plug in a number 2 and get out 4. Or I'd plug in 3 and get out 3 times 3 is 9, right? That's what I mean by a general formula. So we could do the same thing here. What this formula means is, if I put in any vector here, this is what I get out. So let's try some examples. If I put in 1, 2 here, then I just plug in x is 1, y is 2, and get out x 1 plus 2 is 3, 1 minus 2 is minus 1, and 2x is 2. So this is my domain vector. This is the image. That is the image of 1, 2. As another example, say 3, 0 would go to 3, 3, 6, right? So I can put in any x and y and get out this. Now, the question for what I mean by a basis action is this. Is the action of G on a basis here. Well, the basis, let's choose the standard basis. 1, 0, 0, 1 for R2. Okay, well, 1, 0 goes to, well, x is 1, y is 0. So that's 1, 1, 2. And 0, 1 goes to, well, that's where y is 1 and x is 0. Well, that's going to be 1 minus 1, 0. It's going to go to 1 minus 1, 0. Well, let's say I tell you, okay, I want the linear map specified by this. I'm going to call this a basis action. Okay? It's a basis action on this basis here. So I claim I can reconstruct the whole map from this. That means, what that means is to reconstruct this formula. How does that work? Well, if G is linear, G of any vector xy has to equal, well, I expand this arbitrary vector in a basis of x times 1, 0 plus y times 0, 1. Okay, this vector here is the same as, this is just writing this vector as a span of x, y, and then because if G is going to be linear, this has to equal x times G of 1, 0 plus y times G of 0, 1. But if I'm given the basis action, which is what I'm given up here, right? Then I know that this is equal to x times the image of 1, 0, which is 1, 1, 2. And this is plus y times the image of 0, 1, which is 1 minus 1, 0. Then I can, this is in the codomain, I can multiply in the x here to get x, 2x plus y minus y0. Then I can add the two together component by component to get x plus y, x minus y, and 2x. So I've recovered, so this tells me I put in, so therefore I can see if I have G of x, y, then I get out this. So the general formula is xy gets mapped to by G, x plus y, x minus y, 2x. So one point is you can say start from the general formula and find the basis action. Or the other way, you can go the other way, is given a basis action, find the formula here. Okay? So let's do another example. Let's say that I had h of x, y, z goes to x, y, x. Okay? Well, this one has, let's use a standard basis here. Well, this is the formula. Let me, instead of giving you the formula, let me just give you the basis action. Let's say that we have some map H and we have 1, 0, 0 that goes to, say, 1, 2. And 0, 1, 0, we're going to say goes to 1, 1. And say 0, 0, 1 goes to 2, 1. Okay? Then the question is, what does H do to a general vector? Well, we can write, well, you have to write it differently. It's H of x, y, z, because it starts with a 3 vector and maps to a 2, 1. Well, here we can write this as h of x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. Then because h is linear, we can move it in and say this is the same thing as x of h of 1, 0, 0 plus y of 0, 1, 0 plus z of the image of 0, 0, 1. And then because I know the basis action, I can say this is equal to x times 1, 2 plus y times 1, 1 plus z times 2, 1, which equals adding up the terms x plus y plus 2z on the top and 2x plus y plus z on the bottom, and I have the general formula for the map, which is h of x, y, z equals x plus y plus z, 2z, and 2x plus y plus z there. And that gives me the general formula. Okay? Well, that's a project in itself. And in this context, the idea then is that what I can do here is if I know the dimension of A is equal to the dimension of B, then I can construct an isomorphism by choosing a basis action where I send the form of an isomorphism by choosing a basis action where each vector in the basis for A goes to a vector in the dimension of B. I know there's the same numbers, so I can make that map, and then I can get a whole map just from the basis action in the way shown here, and then I can show that that map is one-to-one and onto. Okay, but so I just want you to understand the basis action and realize that if two vector spaces are isomorphic, that means there's an isomorphism and they have the same dimension. And the value of this isomorphism connection is that all the vector spaces can be divided up into groups that all have the same dimensions. For example, there's all the vector spaces that have dimension 0. Well, there's only really, there's of a given type, there's only going to be the 0 vector, but there's ones that are where the dimension equals 1. There's the ones where well, there's actually more of this. There's like sort of the 0 is the polynomial vector, the 0 is a column vector, the 0 is a row vector. This is all the dimension 0, all the dimension 1, all the dimension 2, all the dimension equals 3, all the dimension equals 4. So I can divide up all possible vector spaces into groups and say all the ones with a given dimension are essentially the same. They're isomorphic. There's an isomorphism that says they behave in the same way, they have the same dimension, the same number of vectors in the basis. They just sort of look different. And what I can do is, in each one of these, I can choose a canonical representative. And that canonical representative we're going to choose is our column vectors that we've used so often. So we can, it's sort of like when I have fractions, I have 1/2 equals 2/4 equals 3/6 equals 4/8. I can say there's an endless series of fractions that are all equal, and I can choose one of them, sort of a standard one is a representative, the 1/2, to say that's what I'm going to mean, that these all reduce to 1/2. Here, you can have all these vector spaces of dimension 4, like you could have the M2 times 2 and P3 and R R4 row vectors, and they're all going to be isomorphic to this one. So we can use this as a sort of a canonical representative for this whole class. And that's what we did in the last chapter when we had vector representatives. We sort of looked ahead, or I did at least, and saw that no matter what the vector space is, we can exploit this isomorphism to represent any vector in any of these spaces. We can give it a representation as, say, a column vector with 4 components. And the same with any vector. So it helps us, it sort of helps us to organize all the vector spaces and see that really, in terms of new or different behavior, we just have the dimension to parameterize or tell us what the vector space is. Okay, that's the story with isomorphism. There's a section of the text on this that sort of expands on this and goes over this in more detail. Let me stop the recording.